Now we tried vertically and succeeded. Can we also compute horizontally like this, layer by layer? The answer is yes. Let's try. We still have to go through the height array from the beginning. At height 0, we can't compute, so we store it. Same for the next one. Store it again, all the way until I equals 4. Finally, we can compute this rectangle. And at I equals 5, we can compute this one. I equals 6, this one. So now we find the pattern. When can we calculate? When the taller wall appears. If it's shorter or equal, we can't compute, so hold it. Where to hold it? Use a stack. So we process from the beginning, stack the ones that are shorter or equal than before. Once we meet a taller one, we pop the smaller one from the stack and compute. This is called monotonic stack. There are 3 keys for this problem. First, we need 3 walls to calculate one rectangle. The current one at index I and the top one of the stack. Since we're gonna use this one as the bottom of the water level, we call it bottom. And the third one, the first taller one in the stack, that is left to this bottom. So we call it left. And it's actually the one right below the bottom in the stack. So we need 3 walls to calculate one rectangle. And note, we're gonna put the indices in the stack instead of the height itself, because we're gonna use these indices. And height we can access with these indices. So the current wall is on the right, and the left one is the left side of the rectangle. And the one we call bottom is the bottom of the water level. That's where the water starts pooling. So the height of this rectangle is the minimum of height left and height I. Subtract the height bottom. In this example, height left is 1, height I is also 1, and height bottom is 0. So the height of this rectangle is 1 minus 0 equals 1. And the width of this rectangle is how many degrees between index left and index I, which is I minus left minus 1. So in this case, the width of the rectangle is 4 minus 2 minus 1 equals 1. Thus, the area of this rectangle is height times width, which is 1 times 1 equals 1. That's the trapped water in this rectangle. And after we use this bottom, we have to pop it out from this stack, so we won't double compute. So in this case, actually we can do like this. Bottom equals stack.pop. Pop the top one first and put it into bottom. Then this left will be stack minus 1, which is the new top of this stack. Let's try another example. I equals 5. Bottom is the one on the top, and left is this one. So the height of this rectangle is the minimum of height 5 and height left, which is 2. And height bottom is 1, so we subtract that. So the height of the rectangle is 2 minus 1 equals 1. And the width of this rectangle is the difference between the indices. I minus left minus 1. And here is 5 minus 2 minus 1 equals 2. So the area of this rectangle is 2. And at I equals 6, we do the similar calculation. Alright, the second key point. For each I, we may compute more than once. For this example, we pop the bottom out of the stack to calculate this rectangle. But after that, for the same I, we can calculate another rectangle. Why? Because the new top of the stack is still smaller than current I, which means that one can be bottom again. So we need a while loop. Keep popping and computing until the top of the stack is taller or equal to the current wall. And the third key point, when we finish computing for this I, we need to push the current index I into the stack. Why? Because later, if we find a taller wall, this current I, this wall can be a bottom too. And the code is here. Let's talk about a tiny detail that often trips people up. What if the current wall has the same height as the top of the stack? In this case, yes, we can still push the new one in. Say we push it. Now we've got 2 bars of the same height sitting next to each other. Next, we find a taller wall. Let's call that index I. Now this taller wall becomes the right boundary of this rectangle. And this one is the bottom and this one is the left. Since left and the bottom are the same height, the area of this rectangle we just computed is 0. Kind of useless but harmless. It doesn't break the logic, and the complexity still stays O of n. If you want to keep things extra tidy, you can pop the older one before pushing the new one in. That way you skip that 0 area rectangle altogether. But, and this is the important, always push the new one back in. Otherwise, when you meet a taller bar later, say in this case, your rectangle's width will be wrong, because the stack won't know how far it should actually stretch. So yeah, pushing same height bars is totally fine, but popping the old one before pushing the new one is just a little pro clean code move. Both work, just don't forget to push the latest one in. I know this may sound too much detail, but in the interview you may be asked, so it's worth thinking it through. So the core idea of monotonic stack is like this. We store the ones that we can't compute yet to a stack, until one day we meet one that we can calculate. Then we pop them out of the stack and compute. And this kind of problem all share the same DNA. The not yet values are monotonic, either strictly increasing or decreasing. That's why it's called monotonic stack. Here, the decreasing value for this problem is the height of those indices, not the indices themselves. And the time complexity is O of n, because we only scan the height array once. And the space complexity is O of n too, because we are using a stack. Summary: 2 pointers is the optimal solution, using the least memory, but it's a little hard to understand. Prefix and suffix arrays are relatively easy to understand, and we just have to treat time with space. Monotonic stack is also hard in the sense it's counting horizontally, not vertically. It will still appear in the interviews, so better to understand. Although this problem is too complicated for practice. For example, 739 daily temperature is a good one to practice. These are the 3 ways to solve trapping rainwater. If you find this video fun and helpful, hit that like, drop a comment, say it clicked, share with a friend who's still suffering at this problem. And don't forget to subscribe for more Leetcode hard explanation. This is Taijin, turning hardcore algorithms into sweet little desserts. See you in the next one!